Hello everyone! My name is Connor Smiley, and in this video, I'll be showing off my Pac-Man themed Raycaster that I created over April 2019 for the Ubisoft NXT programming competition. The way this competition worked was contestants were given 3 weeks to expand upon a 2D framework provided to us by Ubisoft, and after that, the contest theme was revealed, and we had just 1 more week to tailor our framework to the theme. I'll go over the framework soon, but first, let's get into the demo. So once the main scene starts, the 4 ghosts load in at each corners of the screen, and for the contest I wanted to highlight my graphics programming abilities rather than my gameplay programming abilities, so hopefully you can forgive the silly pathing system for the ghosts. They simply seek in the direction of the player, and they correct themselves when they run into walls, but sometimes it falls a little short right now since they don't know how to path around the little hole they've dug themselves into. Anyways, you can ricochet off the walls like so, and of course we've got the raycasting algorithm at play. So basically, we're rendering a bunch of lines and simply scaling them accordingly. So if the player is very close to a wall, we're going to draw some tall lines, and if the player is very far away, we're going to draw smaller lines. Also, we've got a dark gray quad as our floor and a slightly lighter gray quad as our ceiling. And if we run into a ghost, it will tell us we got spooked, and we have the option to replay or quit. So let's start things off just once more. We've also got a mini-map in which you can see a top-down view of the ghosts and a little direction vector showing us which way the player front is facing. That's pretty much it for the demo. We've got a couple developer tools in the mix, so I'll recompile with developer tools, and let's check out the bird's eye view of our Raycaster. So by switching this preprocessor value from false to true, we get to visualize our raycasting algorithm. Now you'll notice in the right half of the screen, we get a top-down view. We also see the direction vectors from ghost to player if they're within the player's field of view. And more importantly, we get to see where our line intersects the tile map. Now, the first Raycaster I ever wrote was analytical, meaning it computed the point of intersection directly with the environment. But in this competition, I was given a tile map, and I didn't want to re-represent all of these surfaces by lines. I wanted to reuse the existing code, so I had to come up with a bit of a different raycasting algorithm. So this time for each ray, I would simply figure out the value of each tile I was within, and I would continue stepping until the algorithm found a wall. So this algorithm actually proved to be a little bit more efficient in the sense that it kind of used space partitioning. We didn't have to compute points of intersection with tiles that didn't matter. So I thought that was a cool optimization that just sort of happened accidentally. Now, on to the fun part. I'll explain all of the files in this project basically top-down. They're pretty intuitive. And the other nice thing about this code base is, given the simple nature of this application only being in 2D, this is almost purely mathematical. We don't really dig into any crazy design patterns. For example, I didn't use an entity component system. I simply made my own inheritance hierarchy when it came to game objects. But to start off, we've got a scene manager. Now, there's only 4 different scenes, so it may not warrant an entire scene manager, but I did think this code was elegant and worthwhile to write because it kept things tidy rather than us dealing with state through a plethora of if statements. So the framework had an update and render method, so I simply abstracted those into per scene update and render methods, and when we call our init function, we define each of our scenes like so, using polymorphism so that we can call the corresponding onEnter and onExit functions when we change our scene, and again, just forwarding the update and render methods based on the current scene. So I won't go into instructions and end, they're just displaying very, very brief text. And the main scene is where most of the magic happens. So again, it's still very lightweight. We have our ray engine and our tile map, as well as a player walking through the map, and nothing but a collection of sprites for our ghosts, which are pretty much nothing more than a position and color value that also have a width and height because they're quads. Basically just a POD data structure. So if we look at the body of this, we're initializing our map and our ghosts. This map is not really random because we don't seed our random generator. We don't want uncertainty. When we look at our update function, we're simply calling into the player and the Raycaster updates, and then we're just updating our ghosts in line. So we calculate the direction vector to the player, we pass it through our ricochet detection so that the ghost can traverse along a wall if they run into it because their pathing is very, very primitive. And here is the circle collision detection, just comparing radii between player and ghosts, and if it's true, we end the game. Now, for rendering, we calculate half the height because we know we want to start our rays in the middle of the scene as well as draw the floor and the ceiling to create a 3D effect. So once we have those parameters, again, we forward them to the Raycaster as well as the minimap, and we also want to make sure the depth values of everything line up, so we have to recalculate them every frame. Here we're simply resetting the player in the ghost position, and for the minimap, we're just doing some projection math to scale everything accordingly using GL viewport so that we're, kind of drawing the map basically 20% screen size. Next in line, we have our game objects, or actors, as I referred to them at the time. I guess I was feeling Unreal Engine's naming convention. So, as our base class, we have an entity, which is essentially just a position and an angle. That's all the information we ever really need to pull things off. Then we have a viewer, which inherits from an entity that is nothing more than an entity with a feel of view. And finally, a player, which is our one and only viewer that can show off its speed, and it has an update function, which is essentially just pulling a keyboard or a controller for input. The framework emulated controllers, so I didn't have to worry about that. I simply had to see which input was the case. So if we press left or right, we're going to modify our angle. We basically have tank controls. And up or down just means move forward or backward in the corresponding direction. And I would pre-compute a translation vector to see where the player should go. However, I would then correct the position based off of the ricochet algorithm. So what I mean by this is we would test our map to see if the future position would end up in an invalid tile like a wall. Basically, if our result is anywhere other than like an air tile, we want to negate the component of that translation, so we move along the wall instead of inside the wall. Game test is kind of the base class for this entire demo, where, as I mentioned, we basically forward all the methods in our scene manager, so we just call update and render, which handles things accordingly. We have some math utilities. We've got a line class, which is basically just a couple XY values for start and end. There's not really any interesting methods you can perform on it. Math does, however, have a lot of interesting utilities. Nothing groundbreaking, just simple helpers, degrees, radians, overlap. I can decompose a direction vector into an angle using sine cos, and I've got, again, just some overloads for convenience sake. Can do vice versa, go from direction to angle, dot product, cross product, L1 and L2 norms, so Manhattan or Euclidean, some overloads, circle collision, once again circle collision, and normalization, projection, nothing too fancy, although it's worthwhile noting that I did write some line intersection algorithms only to not use them because, like I said, I wanted to be able to reuse the tile map given to me, so an analytical Raycaster had no place. inside of pathing, you saw the ricochet algorithm briefly, and we also have a completely broken implementation of A star. I'd love to revisit this one day, but it has no place currently. Last but not least, we've got probably the most common class in this game, point, which is really just a two-component vector with some convenience methods in the form of operator overloading. Now we're on to the base framework provided to us by Ubisoft. So starting things off, we have this app header where initially it only came with these draw line and draw quad and draw point methods. So I simply added support for my own data structures to save myself some keystrokes, print if we want some visual text. I didn't make use of playing sounds because I'm not much of an audio programmer. And yeah, just again, key, mouse input, controller input. I don't need to go over that. Settings, defining some width and height, and also sort of their implementation of controller emulation. In main, here's where we do some Windows API stuff to just kind of serve as an entry point for our application. They had a profiler as well as, where is it, this sneaky little function to prove I do not in fact create memory leaks. I was pretty proud because I think I only had like a couple dynamic memory allocations in this entire demo, which was just when I was initializing my scenes. And if I really wanted to, I could do this entire thing without making a single heap memory allocation, but this is more elegant. So darn, I had to make 4 uses of the new operator. Simple controller, again, just very, very standard, simple sound. Tile map, I'll gloss over as well. I added these two things, so this denotes what tile we've landed on, and here we are, just a tile data structure. Right here, they had an algorithm to randomize the map. The goal of this competition was kind of to show off artificial intelligence skills, so basically your AI should be able to navigate a random map, but I said to hell with that, we're making fake 3D, so that I did. And now for the moment you've all been waiting for, the Raycaster. Let's start with a brief overview by taking a look at the header. So, of course, we've got the respective update and render methods. We've separated the rendering across rendering the actual rays and rendering the sprites, since that works fundamentally differently. As members, we've got an index buffer and a depth buffer, kind of stealing OpenGL's naming conventions. But basically what this is a collection of tile values. So basically where the ray intersection ended up, and the depth is just a bunch of ray lengths. Count is the number of rays, thickness is the ray thickness, which depends on the count and resolution. And let's take a closer look at what goes into these calculations. So again, we form the count by dividing the resolution by the thickness. I pass 4 here. We validate this. I thought 4 was a decent value because it allowed for a little bit of blockiness to kind of support the retroactive Pac-Man look, while also still having enough precision to get a good idea of what we're looking at. We size our buffers accordingly and zero out the memory here. For our update, now the split is interesting. We could have done everything all in one step, but in order to preserve the nature of decoupling updating from rendering, I decided to split this up. So in our update method, we basically populate our index and depth buffers, and in render, we iterate through those buffers again to retrieve those values to create our draw calls. So let's take a look at what goes into this math. Starting things off, this line actually doesn't need to be here since our field of view stays constant throughout our application. However, if we wanted it to be dynamic, then this line would be necessary. So we simply calculate the focal length by measuring the triangle that would be formed with half the field of view and the image plane. After that, we get into some actual ray math, where we divide our field of view by number of rays, and then within the loop, we're basically going to increment this angle based on how far along we are from left to right of the viewer. So like I said, we form our ray angle, and then we call our march function, which I'll dive into in just a moment. But basically, this will return us the resulting farmost tile that we've intersected with, and we're going to store that value. So for example, if we intersected a wall or a boundary, we're going to preserve that right here. And once again, we're going to measure the length of the resultant ray and store that in our depth buffer, so that way we know how tall to render our rays. Right here we've got some preprocessor for the bird's eye view draw, which we don't need to get into. It's very straightforward. And the ray rendering is also very, very simple now that we have all our data readily available. So we're going to retrieve our tile information. Tiles have different height values, so that's all that's going into this projection height here, but it's basically the trigonometry math for our focal length, our stored ray length, and whatever tile-specific height values we might have here. And now we simply render a corresponding vertical line at the horizontal position. We start at the bottom of the ray and go to the top of the ray and retrieve the color value from the corresponding tile. And then we just simply increment the horizontal position of the vertical line based on which ray we're trying to render. Now, sprite rendering works a little bit differently. We need to depth sort our sprites just to make sure we're rendering our closest sprite first, otherwise things would look visually incorrect. We get the player from sprite to, the vector from sprite to player, and we turn it into a unit vector. We do 2 checks to make sure that the sprite is actually visible. First, we compare the 2 angles to make sure the sprite is within the player's field of view, and after that, we march a ray from player to sprite and make sure that the ray doesn't intersect with a wall, in which case the sprite would be occluded, so we don't render it. So assuming we have some values here, we simply iterate through it and do some projection math to render the sprite accordingly. So again, we use our focal length to calculate the distance to the sprite and its corresponding scale, and we render it as a quad. Finally, we've saved the best for last, which is our marching algorithm. It takes a ray origin, a ray direction, and it returns the point of intersection corresponding to the first tile that's a non-air tile. So the way we determine this is, of course, we iterate until we find a non-air tile because we want something tangible to render. And what we do within this loop is we compute the ray's overlap along a given tile. Once we know how much overlap there is in each axis, we then compare the rate of change per component. And what we do with this is we want to pick the direction that has the smaller rate of change, because if we use the larger rate of change, we run the risk of skipping a tile. So we scale the components accordingly based on the lower rate of change, and we pass those 2 corrected points along the ray to our tile map function to examine its value. And once again, we either go until we've found a non-air tile or until we've ran out of iterations, in which case we return a border so that we have something to render. That's it. Thank you.